Helen, do we already have live streaming on YouTube or not yet?
Right, yes. Being live stream, yes.
Okay, perfect. Let's maybe wait 1 more minute and we'll start.
Yeah, people start joining at this moment.
Okay. How many people do we have on YouTube? Do you know, Helen?
So far, just 2 people on YouTube,
Oh,
but we have 19 people on the Zoom for now, and one more, 20.
One more. Yeah.
Yes. See,
Okay.
people start joining. Yes. 3 people watching on YouTube.
Okay, good. I don't see more people coming now, so Helen, I think we can maybe start and we can start recording. All right, so we can officially start. So hello, everyone. Welcome to the next Meetup organized jointly by quantum computing groups from Washington, Toronto, and Warsaw. My name is Pavel, and together with Dr. Sebastian Zając, I will be the moderator of this meetup. And today we have pleasure to host our great speaker, Ed Yunis, and he will tell us about compiling resource-efficient programs with numerical instantiation. So sounds very interesting and exciting. Before we start, just a few announcements. So as you can see, this meeting is recorded and it's also live streamed on YouTube. So hopefully the video recording will be later available on our YouTube channel. And we agreed with Ed that we can make this lecture interactive. So if you have any questions, please raise your hand first, and then we'll try to interrupt if there is a good opportunity for this, of course. And you can later unmute yourself and ask your question. You can also just send your question on our chat, and we can also ask if when there is time for this, and there will be also a Q&A session at the end. And all right, so before I give a Zoom to Ed, we would also like to just briefly announce our next events. So next week, Brett Green will tell us about Landau level phases of bilayer graphene. And then in April, Eric Reiter will tell about a serious challenge to quantum mechanics and its applications. Then the next meetup will be in April, on April 20. Dr. Liwen Zich will tell about QA HPC on the quest of quantum AI optimized HPC. And then in May, Dr. Bruna Araujo will tell about moving towards compactification of the many-body wave function using a bottom-up approach. Later in May, Dr. Ed Augusto, I think he's with us today, will tell about quantum reliability, circuit susceptibility faults, and integration issues. And finally, in July, Zeki Seskir will tell about educating to the culture of quantum technologies, a survey study of concepts on concepts for public awareness. Okay, we would also like to thank our partners and sponsors. There are different organizations, so I'm a representative of Quantum AI Foundation, Q Poland, similarly as Sebastian, who is from Q Poland, and Warsaw Quantum Computing Group as well. But as you can see, there are also other partners supporting us. So with this, I will stop, and I will now stop sharing my slides. And Ed, if you are ready, the Zoom is yours. So first of all, thanks for accepting our invitation. It's our pleasure to have you with us, and we are looking forward to your presentation.
Awesome. Thank you for the introduction. Thank you for the invite, and thank you to everyone joining on a Sunday to hear this talk. I just want to double check everyone can see the slides. They look good. You can hear me?
Yes, I can hear you. I can see your slides. I hope that
Awesome.
other folks. Yes, we have confirmations on our chat as well.
Awesome. So now instantiation. I'm going to introduce that concept. I'm going to introduce compiling and what I mean by that, because there's a lot of different definitions in literature now. And then I'm going to showcase some of the cool things that we've done with numerical instantiation, the tools that we've built, and the applications for it. Just to echo what Paolo has already said, you can interrupt me at any point to ask a question. Please cut me off. If you want to yell at me, tell me something on my slide is wrong or that you disagree. I love those. So, please don't hesitate to ask any type of question or make a comment. With that, let's get started. So the motivation for this talk and for a lot of our work is that the quantum hardware landscape is really exploding in a good way. It's experiencing a big boon. There's a lot of companies producing a lot of chips. They're constantly improving those chips. We see an extremely diverse hardware landscape. And this is an amazing thing, because with every iteration, with every generation, there is an improvement in the robustness of these chips. We're one step closer to producing all of the great results on quantum computers. With this comes new features, new gates, new architectures, and most importantly, for our perspective, is new constraints. There's a lot to tune, there's a lot that's changing, and a lot that needs to be made to work with the programs so that they can work on these chips. Now, this increases the burden on the software stacks and compilers to realize end-to-end applications and take advantage of all of these new features. Ultimately, we want our software stacks to be able to translate these advancements to the algorithm layer transparently, so that physicists and domain scientists who build algorithms don't have to concern themselves with the intricacies of the hardware. Now, this is very hard because the hardware underneath is constantly changing and adapting to new features and new technologies. We also don't want our software to limit or guide hardware exploration. We want the hardware scientists to produce what's the best that they can produce and have the software take advantage of that without that guiding it. And I'll expand on that later on, or if there's any questions, I'm happy to talk more about that. So what do I mean by quantum compilation? This is the main part of the software stack that we're going to be focusing on today. But it has many different definitions in literature. The vocabulary is still settling, but it could mean a couple different things. It could mean high-level to circuit program generators. This is more closer to the algorithm layer, where you have some mathematical description of your problem, say a Hamiltonian, and you want to generate a circuit from that description. Could also mean transpilers. So this is taking in circuits, optimizing them for whatever metrics are necessary, solving constraints with the hardware in mind. This is the translation layer. There's also, it could mean control level compilation, which is taking these circuits that are very close to executable or already are executable and mapping them to control signals. This is very specific to a hardware. This part is usually obfuscated by hardware vendors or handled by them directly. We're going to be focusing on the circuit transpilation layer today. That's where most of our tools live. There's a lot of fun and exciting problems in all of these layers, but we focus on the transpilers. That's not to say that the results that we've had are not beneficial to the other layers or that there's no feedback that's necessary. There's a lot of co-design that happens between all of these layers, and I'll touch on that later on in the talk. On top of this, resource-efficient compilation is extremely essential, and this really happens a lot at the transpilation layer, in that we want to not only produce circuits that solve for the constraints of a given hardware, say like gate sets and things like that, but also do it in as little resources as possible. This could be time, the number of qubits or qudits. It could be the depth of the circuit, gate counts, could be many different things. In the NISQ era, this is very much a capability problem. If you use too many resources, you might not have a hardware that's even capable of doing this in terms of it doesn't have the resources, or that the error might be too large to handle. So this is a very important problem. And beyond this becomes a big performance problem. There's also some sliding in between there, that as the first fault-tolerant machines come out, their capability to handle a lot of resource-intensive circuits will gradually increase over time. And so being resource efficient will mean that you'll be able to realize your algorithms on the first generation or the earliest generation possible. This is what it's meant by compilation and resource efficient. So Obviously, we have a tool that helps solve these problems. Otherwise, I wouldn't be here talking. This is the BQSKit tool, the Berkeley Quantum Synthesis Toolkit. It's a very powerful and portable quantum compiler framework. I hope to really convince that point throughout the talk. We have a link here on the right to the website. You'll see this link come up a couple times throughout the talk. This is a launching pad for everything. We have documentation there. We have our GitHub. All of the source code is publicly available. We have all of our publications there. I'll reference some papers throughout the talk. If you miss it, you can go to this website and find all of that there. This toolkit is portable because it handles every gate set in architecture, and that's fundamental to how we do this. I'll explain that in a bit. We have specialized pipelines for widely used chips, and we do generate resource-efficient circuits. This is where the powerful and portable concept comes in. It's not that we are able to translate to a wide variety of different chips, just that, it's that we can also do that extremely well. We have baked in error mitigation. We also have additional error mitigation strategies that complement other tools as well in that regard. And all of this, I really hope to drive this point throughout the talk, is that this concept of powerful and portable together enables an algorithm or a hardware designer to explore the design space of their problem. So I'll have some examples of that later on. BQSKit has been in development now for several years. We have production releases of this. There's a whole host of papers. I'll talk a little bit about some of those works throughout this. We have a bunch of best paper awards. And at this point, between all of our packages, we have over 250,000 downloads. You have users all across the world at many of the major laboratories, at a lot of universities, and at a lot of well-renowned companies. So how does this work? It has turnkey functionality everywhere. If you just want to use BQSKit to do basic compilation, and you can do so much more than that with this tool, but for many users, this is enough. You can just install BQSKit with pip. It's a Python package. It's supported on Python 3.8 and above, on Windows, Mac, and Linux. This can run on your laptop, take efficient use of your laptop, but it can also scale up to a supercomputer. Say you just have a supercomputer in your backyard. Well, you can run this on that. We have a guide online to very quickly distribute this program across a cluster or a supercomputer and take advantage of all of those classical resources to help with the compilation. And if you want to run it in the actual Python script, it's as simple as BQSKit.compile, put your input circuit, get your output circuit. And what goes in can be anything. You can have any gate set, any architecture, anything. What comes out, the same. More than that, though, we can handle qubits and qudits. I'll kind of use those a little bit interchangeably throughout the talk, and I'll try and I'll make a note of it when it's very specific. You can put in states, many states is another, or isometries or things like that. You can put in unitaries, and we're constantly increasing the support of what this BQSKit.compile function can handle. And again, this is just the beginning of what you can do with BQSKit. It's a framework. You can really get your hands dirty and build pipelines, build workflows that are tailored towards your algorithm or your hardware. So all of this is built off of this concept of numerical instantiation or parameterized circuit instantiation. And I hope to argue throughout this talk that it's a very powerful primitive. It's used in algorithms and variational algorithms. It's also used in the compilation side of things. We focus more on, obviously, on the compilation side of things. The process here is that you're taking a parameterized quantum circuit here on the left, and you're finding values to the parameters that minimize some cost function. Most typically, this is you have some unitary matrix, and you want to find the parameters to the circuit that make that circuit most closely implement that unitary. That cost function is given here on the screen, but it really can be anything. It's just the concept of placing values into a parameterized circuit and instantiating it such that it does what you want as best as possible. Now, this is really powerful from a compilation standpoint because it allows us to separate the function of a circuit, what it does, typically the unitary that it implements, or even the state that it maps, from the structure of the circuit, how it does that, what gates are used, where those gates are placed. And so we can separate these two concepts out. If you're given an instantiated circuit, you can calculate its function, you can look at the structure, wipe the slate clean of the parameters and go back to a parameterized circuit. You can then vary these, either one or the other, and in some rare cases both, and I'll talk about that a little bit later on, but you can vary one and try and reinstantiate to get back to something new, to create something better. We'll have a lot of examples of this workflow in concrete cases. The first case, and this is really where this project started with, was with unitary synthesis. And instantiation is at the core of it. On the left here, I have a bottom-up loop that really highlights this whole class of synthesizers in a very simple paradigm. In this process, we're taking a unitary matrix, and we're tasked with finding a circuit that implements that matrix. The most canonical example of this is QSearch, where we build up circuit templates in this tree-like structure. So we'll start with this initial template on the left that just maybe has a few single qudit gates on parameterized single qudit gates on each qudit. We'll try and instantiate that circuit. And if we get a result that we're happy with, then we're done. If not, then we extend this template. And we do this in QSearch by building up a tree. We add a block that includes a 2-qubit gate or single qubit and some single qubit rotations to wherever we want in the circuit. Typically, this is defined by the links. And we build out this tree. We search over this with A star. And then as we pass over a node in the search, we instantiate. Once we find a result that we're happy with, we're done. This is very flexible in the regard that you can change the gate set because you are building up the circuit how you want. So you can choose whatever gate set you want. We represent these things mathematically to the numerical instantiation engine, and so to the engine, it's all the same. And it's also flexible in the regard that if you have hardware in mind that you're compiling towards, then you can encode the constraints of the hardware in this process such that you only build circuits that are already validly mapped. This is what we call topology-aware synthesis. There's many different variations of this with different gate sets, different heuristics for the search, but this really is a canonical example of what we can do. I want to say,
if I can interrupt, because I see that we already have 2 questions on the chat.
Yep.
It's fine for you. So first, I think it's a question from YouTube. Is it correct, Helen? What kind of quantum computer BQSKit can run on? BQSKit.
So the BQSKit is a compiler that runs on your classical computer to compile quantum programs for any quantum hardware.
Okay,
so at this point,
thanks.
I mean, we've done all of the major ones. As new constraints come out, sometimes we have to come back and touch this up. But fundamentally, with this process of numerical instantiation, it's trivial to map to new architectures, new gate sets, and new constraints because of this concept here and this is something that will come up time and time again in the talk as I talk about different methods, is that you really get to change the structure of the circuit or build it up how you would like to. Yeah.
Okay. And there's another question from Kevin. So Kevin, maybe you can unmute yourself and ask.
Yeah, so where do you see this in the next couple of years? Obviously, AI is kind of taking over. In 5 years, it says it'll be the main source for coding. So is this going to be able to accelerate AI like rapidly, pretty much within 2 years?
Accelerate AI. Are you hinting at like quantum machine learning?
No, it'd be like, well, if practical quantum computers existed to begin with, but I don't see any of this technology like really keeping up with what people will want, in the next couple of years. So the question is basically, will this be applicable in some form because AI will be the primary factor and all these other technologies won't be as needed or even necessary?
So we do have a bit of AI in the talk. I think that machine learning large language models and how they affect coding is quite drastic. It's a little bit further away from the quantum computing era. I'm no expert on general ML topics. I think that what the future has in store for that is who knows 5 years from now. But I do think that, I'm starting out small, but as time goes on in this talk, you'll start to see bigger and more impactful applications of this. So maybe we go through the talk, I get to some of the bigger applications of how we've used this tool to solve some real problems. And if you still have this question at the end, I'm happy to take it again and maybe start a discussion that way. But I don't know how to answer it as much as possible right now. I don't know how large language models and AI, how it's affected general programming is going to affect these tools. But let's come back to that question at the end of the talk.
Okay.
Hopefully there's some things that have clarified.
Ed, is it fine for you to answer 2 more questions?
Yeah, please. Yes.
Okay.
Yeah.
Okay, Edgar, you go first.
Ed, thank you for presentation. Do you have any recommendations, IDE or Java? And if you have any experience with Java to work with quantum computers, is there any tool or something, libraries to work with quantum computers?
I don't know that much about Java. I program primarily in Rust and Python. I think this question might be a bit out of scope for this talk.
What about Python? Any recommendation for IDE?
Whatever you enjoy writing in. I've used Vim and I've used VS Code.
Okay, thank you.
Okay, and there's one more question from Jordan, so maybe I will read it. What are you using to benchmark performance and errors on the hardware?
So as of right now, all of this stuff is running classically and being simulated classically, and we do have approximate errors that we introduce on the order of floating point precision, and we're able to measure that by just looking at the ideal versus the target unitary. This is this concept of, is the error acceptable? This is, remember, running classically. We're going to instantiate, we're going to search through this tree. This error is acceptable could mean, is the error equal to 0? Is the distance between the unitary that you want to implement and the circuit that you have, is that acceptable? And we have this set. I talk about this a little bit later on. I talk about verification in larger scopes and more difficult situations. I have a slide on that, but typically this is 10 to the minus 8 or 10 to the minus 10 around floating point precision. I also talk about approximations too later on, and that's, we can dial that way up and see some real cool results.
I think we can go on.
Awesome. Oh yeah, and don't hesitate to cut me off mid-sentence if there's more questions. I'm happy to take them at any time. Happy to talk all day about this. I'm happy to have a discussion either way. Okay, so we have this circuit synthesis paradigm. A few years ago, we realized that we can make a very small modification to this workflow and build a transformation flow. In this case, we're going to start with a circuit that we want to transform or optimize. We're going to make those transformations or optimizations. We're going to change the structure of the templates that we have, change the structure of the circuit that we have, vary the structure, reinstantiate to the original function of the circuit, and keep doing this until either we no longer can or no longer want to. So let me give you an example of that. Gate deletion is the most straightforward implementation of that paradigm. Here, we're going to start in this top left. Can you all see my mouse, by the way?
Yes, we can see it. By the way, there's also one more question, but maybe we can wait until the end of the slide. It's up to you.
I can take it right now.
Okay, so Jervis, could you please unmute and ask?
Hi, thank you for your beautiful presentation. I am more interested in on the bottom-up algorithm. And when you talk about the bottom-up algorithm, do you use like a data structure or like a dictionary or a table to keep track of the items you are searching for? Because according to my experience, most of the time, first of all, the bottom-up algorithm it seems more difficult than the top-down, and to be more efficient, people use a table to keep track of items they are looking for. So in this algorithm, do you do the same? There's like any table or data structure that allows the programmer to keep track of items?
I think there's a point of clarification here. The bottom up here in quantum synthesis refers to building up a circuit from scratch. So in this case, bottom up, you have some unitary that you want to synthesize. You start with a circuit template that has almost nothing, and you build it by adding gates to it up to equivalence, where top down means you're applying fixed linear algebra based, or top down really means that you have equality preserved at every step. So you have some unitary, it's equal to the unitary, and then you start breaking down that unitary from a hierarchical standpoint. But at every step, equality is maintained, where in bottom up, equality is the target. In terms of implementation, there's many different algorithms, and I'll showcase that in a little bit that we have. All of them are implemented a little bit differently. All of them, if I'm going to plug BQSKit a little bit more, all of them are implemented very efficiently in BQSKit. We use for QSearch a frontier to search. We have, we use an A* search algorithm. We actually just use a generic search that you can plug in different heuristics. And many different researchers that I collaborate with actually explore different heuristics. But the typical QSearch is use an A* search over some heuristic that includes the circuit depth as well as the error of it. But this is done with a frontier as you search over these candidates. I hope that answered the question.
Thank you so much. I appreciate it.
There's another question. There's another question from George. How is the unitary given?
This is input. So it's given as an input. So one thing that I think I probably should have made a little bit more clear earlier on in the talk is that these algorithms are, and I get to this in a couple slides, these algorithms are for sizes of circuits that you can work with classically. Now we take this with partitioning, and I'll talk about this in a second, to scale up to thousands of qubits. But this right now that we're working with so far is where we started. We started with 3, 4, 5, 6, up to 12 now qubits, and qudits to higher dimensional qubits. But the unitary is, at these sizes, is still just representable as just a big array or whatever on classical machines. But this is a very useful tool. I promise we'll get to all of this stuff, how we take these and apply these to work into big circuits. Okay, so I'm gonna continue here.
Yes.
Unless there's more questions, I'm happy to take more.
We can go on now. Oh, there's one more question on YouTube. So Helen has just sent it. How many qubits of quantum computer your BQSKit is running on?
So BQSKit is able to compile quantum programs for computers of any size, and we have compiled for theoretical future distributed computers with upwards of, I think it was like 1800 or 1900 qubits. And the limit there is not really our software. The limit is it's hard to find real algorithms that people care about and real architectures that people care about. But this is a very efficient implementation. We can scale up to thousands of qubits. I work with some hardware folk that have their 3 and 4 qubit test beds that they're just testing things out on. We do some really cool things there. I work with some people who are compiling towards hundreds of qubits on real hardware with IBM chips and Quantinium chips, all of them.
Okay.
So I think, yeah, let me, I think it's a couple more slides. Yeah. So I think let me get through the next 4 slides, and then we'll take a break for some more questions. Okay.
Perfect.
So to recap, we have the synthesis workflow where we build up circuits by adding gates and reinstantiating. We have this transformation workflow where we transform an initial circuit until we no longer want to or can. So an example of that transformation is gate deletion. We take a circuit in this top left, and we just remove a gate from it. Now, this is not a valid operation. This does not do the same thing as what we started with. I know some alarm bells might be going off in some of your heads. But what we can do here is we can reinstantiate the parameters to the remaining gates in an attempt to accommodate for the lost gate. So this is us going down to the bottom right here. This doesn't always work. Sometimes you reinstantiate and find that the error that you get out is too high, and so you reject it's unacceptable to you, or you accept if the error is low enough. Now, this very simple strategy is incredibly effective, portable, and flexible. Suboptimal circuits, which a lot of generators do produce suboptimal circuits, this strategy has the ability to remove a lot of gates from them, and we've proven that it can work really well. You take this algorithm and you add it with a candidate selection algorithm of how you choose the gates, and you get a really strong optimization algorithm out of it. Typically, in practice, what we do is we scan left to right, one gate at a time, but we've tried some newer and exciting things that we can do, where we do like multiple gates at a time and things like that, and gives different results. But it's very effective. You just try one gate at a time, remove it. If it's successful, you keep going. Otherwise, you put it back and keep going anyways. Now, this is extremely portable. What I mean by that is it can handle any gate set, can handle qudits, can handle mixed radix even. So it can handle any kind of situation, because at the end of the day, we're just treating this as a mathematical operation. We hand this to a numerical instantiation engine that's performing some form of optimization under the hood, and that gives us a new set of parameters for the circuit. This specific strategy is also extremely flexible in terms of how you use it in the compilation workflow, because it only deletes gates. So it won't change any properties of the circuit that relate to a hardware. It won't, take a mapped circuit and make it unmapped. So you can put this kind of optimization strategy at any point. In fact, in the BQSKit off-the-shelf workflow, we put this in the workflow at many different stages. And so this whole concept of, BQSKit is very portable. And I hope this trend is starting to come up, and that numerical instantiation makes it very trivial for us to work with different types of gate sets, different types of architectures. Now, it's also very effective. This is this concept of powerful, because instantiation performs a global transformation on this circuit. There's this concept of instantiation scope. This is how big of the area of a circuit that you're allowing to change under instantiation. In these cases, it's global. And so you're allowing gates on far ends of the circuit to change to accommodate that lost gate. This is lost on peephole-based optimizations. This is lost on rule-based template substitution kind of things, where you're just trying to pattern match and replace different types of gates. Allowing the whole circuit to change really, really makes this process very effective and finds incredible optimizations that a lot of other compilers can't. Okay, another example of this transformation loop is retargeting circuits. So in this case, we have a circuit on the left, and we want to change its gate set from, say, C naughts to something like CZs. And so we're going to the right here. What we can do in this case with instantiation is take this circuit, go one gate at a time. We take this invalid gate from the old gate set, group it together with nearby single qubit gates, and remove it from the circuit. Then we replace it with several different templates of increasing size that are all in the new gate set, right? And we do this in such a way that one of them is guaranteed to work when we instantiate. Then we instantiate the parameters to the entire circuit to accommodate that change. And we pick the one that is the shortest in depth, or according to whatever cost function you want at the time, and we move on. So in this case, we're going to take the C naught, replace it with these templates, get a new set of templates. Some of them are not successful, some of them are. We pick the shortest one. Now this is awesome because, again, portable, flexible, and effective. Effective because of global transformations. Portable because numerical instantiation, we can handle any gate set. Doesn't matter in, out, whatever. We can also handle heterogeneous gate sets. Say you have multiple entangling gates in your gate set. We can accommodate all of that. In that case, you just enumerate more templates, and we can take effective advantage of that. Yeah, this is also flexible because you can put this before or after mapping. It doesn't change the topology of the circuit. Okay, so we have in BQSKit a bunch of different synthesis algorithms and transformation algorithms. We talked a little bit about both of those. On the synthesis side, we have 6 main ones. We've built a bunch of domain-specific ones in the past for specific use cases, but these are the ones if you want to just import something and use it. We have QSweep, which is a newer one that does one qudit, single qudit pulse optimal decompositions into native gate sets. This is incredibly important because as the dimension of the qudit increases, the single qudit decompositions become very complex. We have qsearch. I talked a little bit about that. That produces optimal results in the 2 to 4 qudit regime. We have permutation aware synthesis, PASS. I'll talk a lot about that later on. It's a really cool thing. Still works in that same regime, and it produces better than optimal results with some very trivial post-processing that's necessary. Again, I'll talk about that a little bit more. These next three, leap, qfast, qpredict, are all awesome. They walk the trade-off ladder in terms of scalability and how big you can do the synthesis and how fast they run. Going down this ladder, going up this ladder, you're going to get better quality results. On the circuit transformation side, I talked about retargeting gate sets, gate deletion, and template substitution. Now here's where all of this stuff, so all of this is built on instantiation. This is where it all kind of gets tied together in how we scale these algorithms to thousands of qubits. We do this with partitioning. So this is, in this example, we're going to take this 5-qubit circuit, and we're going to partition it. By partition, I mean vertical partitioning, not horizontal, which means we're going to group together adjacent gates into block-like structures. So in this example, I'm taking this 5-qubit circuit, and I'm partitioning it into 3-qubit blocks. What we can now do is run our instantiation-based algorithms on these blocks. This overcomes the exponential scaling of numerical instantiation. It does restrict the global view that I discussed earlier, but this introduces a trade-off. As you increase the block size in your partitioning, you will get better results from your workflows. And as you decrease the block size, you will get better quality of, better performance out of the workflows. Additionally, some really cool things about this is that this creates an extremely parallel workflow. Say you have, a 1,000-qubit circuit with 1,000,000 blocks. And you need to run all of these, algorithms on those blocks. They're all mutually exclusive. It's embarrassingly parallel. If you have 1,000,000 cores, you can just all run them and then collect the results back. BQSKit does this push button. This is what I meant when I say if you have a supercomputer, you can distribute this across a cluster. If you have a multi-core system, you can also, just run this on your multi-core without any consideration, without any thought. This will take advantage of those resources. This is all very configurable, but it's very efficient with this. So we take these instantiation-based algorithms, we combine them with partitioning in very clever ways to build what we call workflows. I've mentioned this a little bit throughout the talk. Here I'm going to define it. The workflow does something that the end user actually cares about. Remember, BQSKit is a quantum compiler. It's going to take quantum programs. It's going to compile them. It's going to compile them for quantum hardware. It's a classical program, so it does run on classical systems. The workflows do things you care about on very large circuits. So we can do optimization. So we're just trying to make the circuit as short as possible with as few gates as possible. We can do mapping and routing. We have a few different algorithms for that. There's this PAM algorithm here, which is absolutely amazing. Talk a lot about that later on. This graph is from the paper. At that point, PAM wasn't integrated into BQSKit. Now it is. It's push button. You can just run PAM, and it gives very competitive results, fewer than most commercial compilers in many, many cases. We also have approximation routines. We can do gate set retargeting and do circuit resizing. I'm going to go into detail on a lot of these throughout the rest of the talk. I have one more slide, and I'm going to take a good pause for questions. The first half of the talk will be over. So we have, this was, I think the question came up a little bit earlier. We have push button compiler verification within BQSKit. These workflows lend themselves to being verified in a very nice way. Here's how it works. You can take small circuits up to simulatable sizes on classical hardware. You can calculate their unitaries from the ideal and what you get out of the compiler, and you can compare the errors directly. But how do we handle large circuits? Well, there's this theorem that says the sum of the errors of the blocks give you an upper bound on the actual error of the difference between an ideal and a noisy circuit. So we can verify our transformations that are partition-based with this. We just partition into big simulatable chunks, calculate the errors on those simulatable chunks, and add them up. This gives us an upper bound. It's typically very loose. We can do some tricks to try and make it tighter, and we do in BQSKit. But unless otherwise specified, whenever I talk about error with the compiler, approximate errors or anything along that lines, we're talking about 10 to the minus 8 to 10 to the minus 10 in Hilbert-Schmidt distance. This is very much on the order of floating point numbers. And most of the time, in a lot of cases, it actually comes down to 0 or even very, very, very much closer to 0. With that, I think the first half of the talk is over. The rest of this, I'm going to go into detail on some of these workflows. I'm happy to take any questions, pause for questions here.
All right, great. So first question from Michael. What is your error tolerance and how stable are your qubits at suboptimal conditions?
I don't have qubits. So this is something that you get to input into the program. Remember, we're taking quantum programs and we're compiling them for hardware. So if your hardware has unstable qubits, you can actually encode that in the quantum compiler. And as a result, we can work around that in different ways. Different algorithms have different ways of handling it. This is something that you do have to kind of encode into these workflows in different ways. But yeah, hopefully that answered the question.
Okay, I hope so. So Michael, you can ask a follow-up question if you want. But there's another question asked on YouTube. How can we build error-free and effective Grover algorithms using numerical instantiation?
See, I don't think you can ever build error-free things, and there's no free lunch in quantum computing. So logical synthesis, this oracle synthesis, this is a very important concept for Grover's algorithms and for Grover algorithm generation, is something that is best handled by the domain-specific generator. So I'm going to go back to the first slide here and showcase. One of the first slides, yeah. So quantum compilation could mean many different things. And I think that question you're asking really lies in this area where you have some high-level specification of your program. For Grover's, it might be some logical oracle or some Boolean function or different types there. But that is a program generator that will produce those circuits. Once you've generated those circuits, you can run them through our transpilers, and we can, using this partitioning, all these workflows, then at that point, we can really, really optimize the circuit that comes out of the program generator. In some cases, and I talk about this later on, in some cases, we're actually able to analyze the results that come out of our very great optimizers and take those recognized patterns and go back to the circuit program generator and build better circuit program generators. But yeah, so this like, how do you generate programs for specific algorithms? This does more lie in this level. If your program is small enough, represented as a unitary, you can just synthesize the circuit. But if you're talking thousands of qubits, you have to go through this program layer and then compile with our software.
Okay, so there's another question. What are the real-world applications using BQSKit?
BQSKit is used by many different companies and many different institutes to get the best results out of the hardware that's possible. The real-world application is honestly, it doesn't end. Every day we're finding new ones. This is honestly, it was something that earlier on, when we started this project, we started producing some papers and some results. We didn't know how far it could go, but nowadays, working with more people, collaborating with them, it's honestly amazing and awing to see how much we're actually able to do. The more you know about your specific problem end to end, the more that you can encode it in the BQSKit workflow. If you don't know, you can start with just the BQSKit off-the-shelf workflow and you get amazing results out of it. Real-world applications, you're looking at a couple right now on the screen. I'm going to talk a lot more about them later on. I'm going to go into detail about different applications, different extensions. Looking at PAM on the right here, real-world application is you have some hardware that you want to run your algorithm on. BQSKit connects those dots better than many other compilers because you have on the hardware constraints that need to be solved, and the algorithm is usually generated in a way that is agnostic to the hardware, usually. BQSKit can run our algorithms to solve for the constraints, move the circuit, the program around in such a way that it is executable on that hardware. And you can see here, this is going up to thousands of qubits. So this is, and we do this incredibly well. I talk a lot about PAM later on. Approximations is also another one. This is incredibly important in near-term computing, which is near-term quantum computers have a lot of error. And there's a trade-off in how much error we allow in the program generation, in the program compilation, and how much we can use that extra error budget to produce better circuits that have shorter depth, but maybe higher error. There's a trade-off because shorter depth means less error when you go to the hardware. We have some clever algorithms that do that. You're looking at, this is a Heisenberg simulation. And our approximation, this 8 sample line right here, tracks the ground truth much better than the baseline.
Okay, there are 2 more questions. Can BQSKit run in any of notebooks?
In Jupyter Notebooks, yes, definitely. So depending on how much time we have left, we have a tutorial online that you can get through the link. I have it up, ready to switch over at any point and showcase it. That's in a Jupyter Notebook. You can run this and run it in a Jupyter Notebook, yeah.
Okay. There's one more question. I'm not sure if it's relevant to this talk, but maybe you can try to answer. Would you recommend QFast over Leap and QSearch A star?
That's a very good question. So there is different regimes where these tools will win over the others. If your circuit is small, or if you're willing to wait longer for the big circuits, QSearch will always give you better results than Leap and QFast. QFast and Leap are great tools that allow us to scale these problems. So to introduce them, I didn't really introduce them too much. Leap has an extra heuristic in the search that allows you to reduce the amount of backtracking you do. And as a result, we're able to go further in the tree quicker. Whenever you go further in the expressive regime, go deeper, more gates, more expressive, the instantiation will have a higher chance of success. So we find solutions a lot quicker. There's a trade-off in quality. QFast is the next step up from that. QFast doesn't do the search anymore. QFast does, it conflates the search into the numerical optimization, into the instantiation part. We have a way of representing variable location gates here. And as a result, we don't do any backtracking at all. We move very quickly and we have very expressive circuits. This produces good results, slightly worse than Leap, which is slightly worse than QSearch, but it does scale better. QPredict is very experimental. It allows us to scale up a lot larger by trying to predict the next placement of gates. But when do you use them? If you're experimenting, try them all out, see which ones you like the best. They're all, import from Biscuit QSearch, run QSearch, import, Leap. The tutorial goes into detail about these things, one of the tutorial notebooks. But yeah, I think it depends on your problem. Yeah, it definitely depends on your problem. It also depends on the workflow. So this is for direct synthesis. When you look at the workflows, some of them don't need to scale very large, like PAM works with 3-qubit blocks. And so QSearch is perfect there. It actually uses PASS, which uses QSearch, but this is very workflow and algorithmic dependent. Try them out. Typically, it goes with the block size.
Okay, good. There is one more question from Jordan. Jordan, maybe you can unmute yourself and ask.
Sure. Hello.
Mm-hmm.
So there was something that was published probably about a week ago about researchers uncovering inaccuracies in qubit rotations on IBM's public quantum computer. And I wanted to know, is this something the compiler can compensate for once these things are published and we're aware of them? Or is this something the hardware vendor IBM will work on mitigating on a future release?
It's an awesome question. Hopefully both. To answer the question plain and simple, the gates themselves should be implemented as good as possible by the hardware. This is what I meant earlier on, that the software system shouldn't really guide the hardware development. Hardware folk, they should do what they do best, produce the best thing possible, let the compiler take advantage of it. If the best thing possible currently is a rotation with coherent errors, these like over rotations or under rotations, then that can be encoded in the synthesis. Like if you can define your gate to be anything you want here, right? So if you can define your gate with the delta over rotation, the synthesis will actually turn that error, and we've done this, turn that error into valid computation, and potentially in some cases reduce the depth of the circuit because of that error.
Awesome, thank you.
When it becomes stochastic noise, it becomes a little bit more complicated. But with coherent noise, like we've done this, we can do a lot of cool things there.
Okay, I think we can go on.
Okay. Permutation-aware synthesis. I've talked about this a little bit. Let's talk about it in detail. This is better than optimal synthesis with post-processing. This is kind of our champion right now. In Biscuit, we use this to do permutation-aware mapping. Both of those are just amazing tools with an amazing insight. Let me motivate the problem here. Again, I'm working with small circuits just to motivate the problem. But say we have this 3-qubit QFT, the optimal implementation, this is without swaps at the end. The optimal implementation is 60 knots. This is an all-to-all connectivity. So if your hardware, you have 3 qubits on your hardware and they're fully connected, great, you're done. You don't need to do anything. But if they are linearly connected, in this case, 0 is not connected to 2, so you can't have these C knots here interacting with one another. This is not a valid hardware native gate. You need to do mapping. You need to take this and map it to take the circuit and map it to something that works on this architecture. Now I have here the optimal map with OLSQ. This is a great tool that solves for the optimal placement of swap operations that are valid on the hardware to make sure that the entire circuit is executable. This is very much a traditional approach to compiling this circuit from an all-to-all connectivity to a linear connectivity. However, we get 9 C knots. Let's see if we can do better. So I have here, again, the optimal map. This is the OLSQ algorithm. And this is any traditional mapper that inserts swaps. This is the best that you can do for this algorithm. QSearch, talked about that. It is able to do topology-aware synthesis. So this is completely looking at the circuit, rebuilding it from scratch, from its unitary. So we took the function out, we varied the structure, we built up the structure in a way that already maps to this linear architecture. And what we found is that we can produce this circuit with 6 C knots. There's no swaps here. The communication is implicit in the algorithm itself already. And this is linearly connected. This is topology-aware synthesis. Now we have permutation-aware synthesis, which is, can we permute the function? So now we're varying both structure and function. This is one of the rare cases where we do that. We're saying, is there a different thing that we can implement that very much relates to what we want? In this case, we're going to allow the input or output, or both, qubit ordering to vary, to permute, as we're synthesizing the circuit. And what we find is that you can do this QFT algorithm with 5 C knots. This is the best I know of for QFT3. For linear architecture with permutations, if you allow the output qubit ordering to rotate. Now, this is, it requires post-processing. When you read this out of your quantum hardware, you're going to get some bit strings. It's very trivial to resolve these, though, because all you have to do is permute the bit strings. That's it. If you get 101, you get 110 is the actual real result. That's permutation-aware synthesis. The cartoon for it looks like this, where regular synthesis takes this unitary and produces a circuit that implements that unitary. Permutation-aware synthesis injects identities split up as the transpose of a permutation times the permutation into the circuit. So this is still equivalent, right? These are identities, these cancel out. But we're allowing them to group, to associate in different ways. So in this case, we're going to associate the ones in the middle and produce something that is different than what we originally wanted. And these transposed permutations can actually be factored out to the qubit boundaries. And so we get this result when we synthesize this block in the middle. We get a shorter circuit, but now we have input and output qubit orderings have changed. We repeat this process for different permutations. We find the shortest one. Permutation-aware synthesis. Are there any questions on this? Okay.
I don't see questions, so I think we can go on. So
how do we scale up pass? One last thing. We have to try out many different permutations here. And the number of permutations grows factorially with the qubit size. So that creates a challenge. What we can do, though, is utilize pass with 3 qubit blocks to perform permutation-aware mapping. So what I mean by this, take your big circuit. This is now back to those 1,000 qubit circuits. We partition it, similar to how we've done in the past. Partition these circuits into blocks. And take these blocks. For every single block, we synthesize it for all the different permutations, for all the different potential architectures it could land up on. So we have all of these things done offline, and we have all of these for every block, every different possible permutation synthesized. What we do now is then we map the algorithm with a generalized Saber algorithm. So as we go from left to right, we're adding swaps to make these blocks executable such that they line up on qubits, physical qubits. The logical ones line up on physical ones that are connected in the hardware. When a block becomes executable, we move it from the not mapped to the mapped section of the circuit. As we do that, we have another heuristic. This is the permutation we're mapping. We have a heuristic that selects the best permutation for that spot in the circuit, for that state of the algorithm. Previously with permutation or synthesis, this was just what block is the shortest in terms of depth or gate count or whatever cost function. But now the permutation that you select, the output permutation, actually affects the mapping. And so there's a balance in this heuristic in how much gates we're able to reduce on the block, as well as how that permutation will affect the mapping going forward, such that we insert fewer swaps to make the entire circuit mappable. And this works incredibly well. So to showcase some results, we take a bunch of these algorithms. These are algorithms from many different areas of quantum computing from across different sizes. And we're compiling them to the IBM 127 qubit Eagle chip. In the paper, we compile to many different architectures, many different hardware. If you're curious, definitely take a look. This is that architecture. You can see these are the physical qubits and the connectivity of them, so that gates can only be applied between connected qubits here. Comparing to other algorithms, see massive reduction. I think there's only one of these cases where we were slightly worse than Ticket, which is an amazing compiler. Here we have BQSKit separate from PAM because when we were writing the paper, it was its own separate thing. At this point now, they've been integrated, and so that they're one algorithm. But yeah, that's why they're separated here. But yeah, we see massive reductions. We're able to map things better overall. In a lot of cases here, there's just a reduction that we're able to find that was not previously able to be found. And we see some massive improvements from other compilers. Building on this even further, there's a cool thing about PAM that I don't think exists in any other mapping algorithm out there right now, is that it can take a circuit that is already restricted enough that it can map directly to a hardware. Think you have a linearly connected algorithm and you're mapping that to all, right? Then you don't need to do any mapping. There's no swaps that need to be inserted. You can just place that circuit directly on the hardware as is with a one-to-one logical to physical mapping. PAM can actually take advantage of the increased resources to produce more efficient circuits. Because we introduce permutations, we get to move things around in the circuit. And now all of a sudden we can take linear and map it to all and get better results. So this is really apparent over here on these TFIM and TFXY model simulation-based circuits. These were linearly connected and we're mapping them to all in this case. All comes up a lot on trapped ion, quantinuum, ion Q type architectures. In these cases, all of the compilers were not able to see any improvement. BQSKit saw a small amount of improvement with synthesis, but we see massive improvements. More so, again, I think we're getting better results in every single case except for this Hubbard. This was a hard circuit for synthesis to work with. Also, another cool thing is that the QFT5, no algorithm was able to find any reduction on it, except for PAM. We saw another reduction, and this is better than optimal. This is where we get this concept of better than optimal here. Yep. Any questions on PAM, PASS, or any of this?
I don't see. Oh, there's one question from Jordan. So Jordan, you can unmute again if you want.
Yeah, so for PASS and PAM, are you implementing like classical machine learning techniques for these optimizations? Is that what's going on here?
In what step? So this synthesis is very similar to Q-search. We're just giving it a different target. If you give me a unitary input, we'll come up with a bunch of these ones. And that Q-search is doing numerical, that it does instantiation under the hood. That instantiation typically uses numerical optimizers, like, that are very common, gradient descent type things that are common in machine learning applications. There's other ways that machine learning can come into play, which is speeding up the synthesis by selecting better starting points. I talk about that a little bit later on. I hope, hope that answered the question, or if there's something specific there, let me know.
Oh yeah, and so for when you're combining these into this new circuit and seeing where you can map this, isn't that a place too that you can use machine learning and some forms of AI to find optimal improvements there in optimization when you're looking at crunching the numbers here in terms of the numerically accurate and speed ups for those mappings, basically, because you are combining all of those circuits and those the mappings, correct?
Yes. So there is two different decision steps in this algorithm. There's where do you place the swaps, and then you pick the permutation. The synthesis step we do for single differentiation because looking at circuit in the map, so have everything on ready to go. There is potential for ML in speeding up the synthesis aspect, and I talk a little bit about that later on. In terms of where to place the swaps, I think that's a really cool idea. I know that this permutation aware algorithm is not, it's not dependent on how you place the swaps, just that, this is a heuristical method. So if there's an AI method to kind of give you better insight on how you place the swaps with further look ahead, that's definitely a good idea.
Thank you.
Okay. There's just one comment from Kevin on the chat, but it's not a question, so it's yeah. Okay. Anyone would like to add something or ask about anything? I think we can go on.
Okay. I hinted at this also a little bit early on, algorithm compiler codesign. So this is, I'm going to talk a little bit about ML here, but I'm also going to look at how we can take the results of our compiler and learn things from it that influence the algorithm design stage of the software stack. I'm going to start off with a couple different times that this has happened in very incredible ways. In this case, I'm not a physicist. I'm just going to throw that out there right now. I've worked with great physicists on this project, and that was a lot of fun. But yeah, if you have questions about the antiferromagnetic Heisenberg model, I might not be the best to answer it. But this is an algorithm where we were trying to do real-time evolution of this model, the antiferromagnetic Heisenberg model, on a two-dimensional Kagome lattice. This was done in a way where you have 3-qubit building blocks, and the algorithm generator produced 9 C0 building blocks. And so you get the circuit. We'd optimize it with BQSKit. We found that we were able to reduce it down to 8 C0s many times, and they all had very similar structures. Identified the pattern, that's this pattern right here, that was completely different than this 9 C0 building block. There's non-intuitive transformations to get there. We're able to take that and code that back into the algorithm generator, and now this generator produces circuits using this 8 C0 building block and gets the 8/9 or 9/8 reduction out of that. So this was one example. I have a couple more here. Another time that this came up is that a little bit different. We were manufacturing a pattern in this case. We were tasked with doing qudit GHC state preparation. So we have higher dimensional qubits. These were qtrits, qquarts, even qquints. This is the D equals qtrit, qquart for 4, and qquint for 5. We did this in a way called kernel cycling, where we have this Bell state to GHC state block that we wanted to synthesize. And we found that you prepare a Bell state on these 2 qubits, you do this Bell state to GHC, and then you can cycle 1 qubit out, put 1 qubit in, and you get the same Bell state on those 2 qubits. And you can keep doing this to build up a GHC circuit. So we synthesized this block. And we did it for qtrits, qquarts, qquints, and we found, hey, look, there's a pattern there. We took that pattern, wrote it down, proved it constructively for NED. So now with this, we were able to prove that with this new gate set, this is this paper here that was focused on these new gates for higher dimensional quantum computing. With these gates, you can build qudit GHC state preparation circuits bilinear in the number of qudits that you have, as well as the dimension of those qudits. This is really cool. One other, and this will be the last time I talk about that, I bring up like a concrete example of this. One other TFXY TFXY, XY, IM, and TFIM Hamiltonians. We were doing time evolutions of these, real-time evolutions of these models. And as you scale up the time in the simulation, the circuits would grow linearly with depth, or linearly with time, the depth would grow. When we would optimize these circuits with BQSKit, we found that after a certain time step, we were getting the same result no matter what. We were able to reduce it more and more every time. We worked with some amazing mathematicians and physicists on this problem, and we're able to recover a algorithm that is able to take now these linearly growing evolutions and compress them to a constant depth, no matter the time. So it's constant with the time here. And this led way to the production of the F3C++ generator for these models. This is an amazing piece of software. You can use this to generate circuits that are constant in depth with the time for these Hamiltonians. I think there's a few more that have been added since this project, but it's really cool to see these results go back and influence the algorithm generation there. I'm going to talk more about the ML stuff here in a second, but is there any questions about any of this?
There's one question from YouTube. From where can I try out PAM algorithms?
So if you do BQSKit.compile, I'm actually just going to go back. You pip install BQSKit. It's a Python package. BQSKit.compile. There's a comma optimization level equals. If you put optimization level equals 4, I know they typically go up to 3, but hey, PAM really deserves the optimization level 4. If you put optimization level 4, you'll be compiling this with PAM. We have and I'll showcase this depending on time. Definitely show you the link and everything. Where is it? Right here, biscuit.lbl.gov. You go there, you go to our GitHub page. There's a BQSKit tutorial. In the notebook, it talks about how to use the BQSKit compile, the different options. It shows you examples for that. Set the optimization level to 4, you're running PAM. That's it. If you inspect the code, there's detailed workflow there that you can mock with and play around with if you want to get really into it. Yeah.
Okay, I don't see more questions now, so I think we can go on.
Okay, so we did all of this. We find that we're able to learn a lot about the structures of circuits on what comes out of our high-quality synthesized circuits. So we asked the question, can we do this automatically? We started with this question, can we learn quantum circuit structures? Can we predict a good ansatz for any given unitary? So we did this by just collecting a bunch of data to start, as with many different ML projects. So we collected a large data set of unitaries. And it's important here to note that these unitaries, these functions, come from partition circuits that we care about. If you use random unitaries, it becomes a lot harder to learn anything, if there is anything to learn about random unitaries. But the unitaries that come from real circuits that you want to run are far more structured and far less dimensional, thinking like principal component analysis stuff here, far fewer dimensional than random unitaries. And as a result, we can learn some really cool things with them. And I'll show that in a second. So we collected a bunch of data. We enumerated all the circuit templates that a number of them, a finite number of them. And then we instantiated each template for all the unitaries. So we did like a Cartesian product here. And we just kind of recorded which ones were successful, which ones weren't, and we tried to learn that. We looked at some patterns first. So we asked, do we see patterns in the templates that come out of these unitaries when we scale up the algorithm? So here we're taking those TFIM circuits. We're looking at 8, 16, and 50 different 50 qubits, so different sizes of the problem. We found exactly that, yeah, the template that comes out of them in many cases is the same. And so yeah, I apologize for the blurriness of the picture, but yeah, we're able to see that there is a lot of repeated structure in these circuits, even as they scale with size. The next question we ask is what happens when we compose algorithms? Because some of these things that I've been mentioning, like QFT, are typically building blocks in bigger algorithms like the Shor. And so the Shor uses QFT a lot. It also uses other things like modular arithmetic. But if we look at what comes out of the QFT circuit, so this is the light bar, and we look at what comes out of the Shor circuit, we count how many templates we see that there's a large overlap between the templates that we see in the QFT and the templates that we see in the short. So there's definitely a lot to learn here. So we did that. We tried to build a neural network that can predict a circuit structure given a unitary function. In this case, what I mean is a circuit structure that can instantiate to that unitary. We were able to learn some very interesting properties. We trained this, and we built this algorithm called QSeed. So what QSeed does is it takes a target unitary, runs it through our model. That gives us a seed circuit. This is a template to seed the synthesis search with. So if you remember, QSearch has this big tree. Starting from the beginning every single time means we do a lot of instantiations to get to the result. If we can start very close by, if not exactly on, a solution structure, then we can speed this whole process up significantly. Instantiation accounts for most of the runtime, so the fewer instantiation calls directly relates to how much faster this is going to go. We found this very successful. So we're looking at two graphs here. On the left, we have the solution quality. We wanted to make sure that the outputs, again, very sorry for the blurriness of the images. I don't know what happened there. But so on the left, we have solution quality. We wanted to make sure that, if you predict something that's really bad, then there's a higher chance that it'll be successful, but you'll also end up with worse circuits. So that's no fun. So we wanted to make sure that the quality was good. On the right, we have the speed up. So let me call out a couple things here. We measure speed up in the number of instantiation calls, because again, that's almost directly related to how fast this process will take. Full bottom-up synthesis, read QSearch, requires an average of 12 instantiation calls for a bunch of these blocks. QSeed was able to reduce that down to 2.4 instantiation calls. So that's an amazing speed up. Moreover, that the solution quality very closely matches the gate count. So this is awesome. We were definitely able to learn a lot. We were able to use that information that we learned, use that model, and integrate it into our workflow to speed everything up and maintain quality of solution. Okay, any questions about this?
Is QSeed available for people to use on GitHub or something?
Yes, so QSeed is currently going through a transformation right now. The student who led this, Matthias Sweden, he is part of the BQSKit project. He has a QSeed variety that was done for this project on his GitHub. We are currently working on integrating that into BQSKit. There will be a release coming very soon. We're actually putting the final finishing touches up on it, but you can definitely use it. He has instructions, he has README. It's definitely usable from his GitHub. Just a deeper integration into BQSKit is still a little bit ongoing. Yeah.
Okay, good. Thanks. There's one more question from YouTube. How is generalized Saber used for PAM?
So with PAM, what is it? You still have to apply this global mapping algorithm. It's a heuristic algorithm in the sense of the blocks are not always executable. The permutations help with the swaps that you have to place, but you still have to place swaps. And so where do we place swaps? We use a generalized Saber heuristic to determine that. It's generalized because we're working with blocks, and the Saber algorithm, the heuristic there, doesn't accommodate for larger than 2 qubit gates. And so we had to modify the heuristic quite a lot, actually, to make it work with blocks. Introduce all sorts of local minimums and all this fun stuff, but we handle all of that. Hopefully that answers the question.
Okay, I don't see more questions now, so I think we can go on.
Okay, cool. Great questions, by the way, everyone. Please, continue to bring them on. I don't mind jumping around, interrupt me. We talked a lot about compiler or algorithm compiler co-design, how there's some feedback between the algorithm generation there. Let's talk a little bit about the compiler hardware co-design. So this is one example already came up in a question earlier, which was, if we know something about the errors on the gates that are actually being implemented in hardware, you can stick that in the compiler. I didn't actually bring that up in the slides, but that's definitely a use case. This concept of feedback between these two steps of the software stack. So one thing to realize here, I'm going to introduce a very big graph here, is that Not all gate sets are equal, and they're very algorithmic dependent. So let's look at this graph. There's a lot to unpack here. There is two graphs, top and bottom, two bar charts. Each set of columns aligns with a different type of algorithm. They're all labeled here on the bottom. And these are different families. I think there's I might be wrong here, but I think this is just like a bunch of different sizes of this type of algorithm. On the top, we plot them compiled to the different gates that are available in hardware today, in some hardware or another, right? Some of them will implement CZs, some of them implement ZZs. This is like Quantinuum. ECR is IBM superconducting type. Sycamore and square root iswap, that's the Google FSIM family type of gates. The y-axis on both of them, we plot their relative count to the optimized C0 variety. So a 1 here means that these gates for this algorithm are equivalent in strength to the C0. Higher means that you require more of those gates for that algorithm. And what we see is that there's a wide variety of results here. They're not just like one thing that says some gates are more expressive than others and that's better and something along that lines. More so, not all gates are created equal. Oh yeah, the bottom chart is for theoretical gates that have been proposed in literature, but not implemented as far as I'm aware. This is the B gate. B gate is incredibly expressive in that it only requires 2 of them to implement any 2-qubit unitary versus 3 for most other gates on this chart, many more for these ones. The 4th root and the 8th root of C0 are very low entanglement, potentially proposed to be high robust, high fidelity gates. I'm not aware of them being implemented. They might have been implemented since we produced this graph, but the idea is that you require a lot less to implement these, and as a result, the gate times are faster, they'll be higher fidelity. What we see is that all of the gates are pretty much equal in representative power for these families of algorithms. And this is very important to note because, if you're able to do the QFT algorithm with the 8th root of C0 versus the individual C0, it's about the same, just slightly more. And this is a much more robust gate. That's definitely something to consider when you're implementing the gate set on hardware. But that's not the case for all of them. We see that for different algorithms, we see much higher use of this 8th root of C0. The low entanglement gates tend to struggle in this area. So these are these 4th root and 8th root C0s. We see that we require a lot more of them on these algorithms. More so, these FSIM family of gates, we also see that we require a lot more. So the goal, the key point here with this graph, I know there's a lot of information to look at here, is that the ability for a gate to express a circuit really, really varies by the algorithm. So gate set designs include algorithms that you target hardware with that. So we asked, can we take all of the compilers and build a methodology and a corresponding model to answer potentially important hardware design questions? Now, we have a couple questions here listed. How much should I improve my gate fidelity to outperform other machines? When do we see a boost in performance from reducing single qubit gate counts? And it's kind of surprising that in some situations with specific hardware and specific algorithms, single qubit gate counts are not that important to optimize for. In some cases, they don't really make that much of a difference or even any difference at all when comparing different machines. Does offering hybrid gate sets improve my machine's ability to express the circuit? So all of these really require the ability to compile a algorithm in a very efficient as possible way to many different gate sets. So you do need these synthesis type algorithms that we've discussed before. But in our methodology, we actually do a search over different compilers, different workflows to really make sure that we're producing the best circuits for these types of analysis. There's a paper that's out now on arXiv. It's a great paper. It goes into detail about a lot of these questions. There's a lot of data there. There's a lot of analysis and guidance for how to use this. But I'm going to focus on this last one here. So again, I know this graph kind of really got hurt by the blurriness. I don't know what happened there. Let me explain what's happening here. So we're looking at hybrid gate sets. These are heterogeneous gate sets that have multiple entangling gates in them. We have a couple sets. We look at CZ and XY, and we look at the striped one is the combination of them. We also look at Sycamore, square root isop, and the combination of them. That hybrid gate set I'm pretty sure is available on the Google architectures. And then we look at the whole FSIM family. This is a continuously parameterized 2-qubit gate. It's unique in that regard. Not many are like that. And it parameterizes many of these different gates. These are all kind of instantiations of that FSIM gate. So we compile for all of these different ones, the individual gates, their hybrid counterparts, and the FSIM family. What we find is that hybrid gate sets are not always a win. Looking at different algorithms, more times than not, it's usually not a win. And so this is very important from a hardware design perspective, because more gates to tune up and calibrate increases your calibration time, increases the manpower needed to maintain machines. Having fewer gates to tune up is I think, a good win. And if you're not losing anything from the algorithm side, that's great. There's also another really interesting thing happening here, which is that the FSIM gate is able to outperform everything pretty much, I think, in a lot of these cases. And so this raises the question, is there potentially different instantiations of the FSIM that when you build a hybrid gate set out of those, that you're able to mimic these improvements in results, right? And those might be non-intuitive gates that the compiler can help answer. That question needs to be answered alongside a hardware developer, because there is constraints in terms of what can actually be instantiated in reality. We can't just pick, 2 random gates and say these are the best ones, or 3 or 4 random gates and say these are the best ones. We have to really consider the constraints of the hardware here. But there's definitely a good question to ask, which is, what is the right instantiation of FSIM, or the right hybrid gate set to get the best results out of algorithms? This is really kind of breaking abstractions along the entire software stack here as we ask these questions. That's all I have to say here about the compiler hardware design, but there's definitely a lot that we can look at when we work with hardware folk. I'm going to take a second here if there's any questions.
I don't see any questions, but let's maybe give a bit more time.
There's more questions that come, don't hesitate to cut me off or interrupt me. We'll continue moving on. How are we doing on time? Okay.
I think it's quite fine.
So let's talk about circuit approximations. This is going to be kind of a tone shift here. This is looking at an error mitigation strategy using these compilers, these approximate compilers, dialing the approximation noise all the way up. Question is, why should we even do approximate quantum circuits to start with? So we look at these process matrices. We look at what we're synthesizing, what the target was originally, and in these cases of approximate, we're going to allow a very large difference between what we synthesize and what we wanted to synthesize, what the target was. What we find with this is that we're actually able to get a lot shorter circuits this way if we allow the error to grow, the allowed error in the synthesis to grow. But this ends up, with some trade-offs, ends up matching the quality of the output that you get on the hardware on NIST devices, because there's a trade-off between, the gate errors with deeper circuits and the approximation error that you allow in the synthesis. And we're actually able to tilt this in our favor quite a lot. So that was the initial idea, but we took that and built a very clever workflow out of it. So we have this concept here where, what if we build a bunch of different approximate circuits such that they all average to what we want as good as possible? In this case, we're looking at a couple different, this is a very, very high level view of the space of unitaries. This is a very highly dimensional space, but this is very much cartoonish to describe the notion of what we're doing here. These teal squares are synthesized results, and the target is this red cross, right? So you want really to be on that red cross as much as possible. But if we allow some error away from the red cross, we can potentially get shorter circuits. Now, if we synthesize a bunch of these such that they're kind of on opposite ends of the red cross, again, that's a very hand-wavy notion right now, but we synthesize them on opposite ends of the red cross, and we take the average of these results of the return of the outputs from running on actual quantum hardware, we get closer to the target that way. And so with more samples, we're actually able to get closer and closer. It's very much empirically driven. We are working on theoretical proofs, and there's a lot more to come in this coming soon, but I won't talk too much about that. What we've done with this is build this Quest algorithm, and this is runnable through BQSKit. Here's the paper down here if you're interested. what we see is that by allowing these reduction or these approximate circuits, we see a depth reduction pretty sizable in the range of 30 to 80%. And this is after all of the other optimizations and compilation steps and everything that we've done before. So this is just kind of an extra gain. And when we take these averages, that the output distance is actually very close to the ground truth. These are definitely workable in a Niscara. And looking at the Heisenberg circuit specifically, we're able to see depth reductions of up to 85% for the 16-qubit one. With a 4-spin one, we ran this on a quantum hardware at the time. I think this is a couple of years old at this point. But with 8 samples of 8 different approximations, and we take the results and average them, looking at the actual end-to-end outputs of these algorithms, we're able to track the ground truth a lot better than the baseline. And this baseline kind of just goes to 0 and is just more or less random at this point. So this is a really cool result. That's all I have to say about this. But definitely check out the paper. And if you're interested in this, stay tuned. I think we have a lot more coming out soon. Any questions on this?
Okay, I don't see any questions now, but let's maybe wait a few seconds. Okay, I think we can go on. Maybe there will be. Oh, there's one question. There's a question from Jervis. Jervis, maybe you can unmute and ask.
Hi, my question is about the concurrency and parallelism of processes. I wonder if it's applicable in quantum computing, and if yes, how do you arrange gates to implement or to obey to the rule of parallelism or concurrency or processes? Thank you.
So are you asking about parallelism on a quantum machine?
Yes.
Like if you have, say, like a 20-qubit chip, but you have 5 4-qubit algorithms, can you place them all together?
No, my problem is just in traditional computers, we have parallelism of processes or concurrency of processes. For example, now people are using parallelism like to speed up the computing processes. And I'm wondering if the same procedure is applicable in quantum computing. If yes, how do you arrange gates to implement parallelism of processes in quantum computing?
So I think this concept of, say, multi-core or parallel systems on quantum computing is a bit early to speak very positively about that with high hopes. There is this notion of distributed quantum computing where you have many chips that are connected either classically through classical communication channels or quantum communication channels. There is potential that these chips could be running things in parallel. It's the same concept of if you have, say, 20 qubits, your qubit or qudit is really a notion, or it's a computational node almost. It's hard to draw these analogies, but you can separate the chip based off of grouping together qubits. So the chips will have connections. This does introduce a lot of errors. There's crosstalk on all this kind of stuff because quantum computing, these are these, as much as you try and separate them, if they're still coupled on the hardware, then there's gonna be potential interactions between them. I think it's a bit hard, especially at this early stage in quantum computing development, to draw analogies between classical multi-core parallel systems or distributed systems to quantum distributed systems. But I think that's like probably the only way that you can do that right now is if you have, say, four qubit circuits that you want to run, you could potentially group them together as one 16-qubit circuit and run it as a 16-qubit circuit and then split up the results. Do you get better results than if you just ran four 4-qubit circuits individually? I don't know. If you do that though, and you get a 16-qubit circuit, you can definitely optimize that with BQSKit. You can use PAM, you can use all of these things to try and reduce that as much as possible. Maybe that gives you better results than doing the 4-qubit circuits individually. That's It's definitely a good question.
My second question is, how do you group those qubits or tips to apply the distributed quantum computing? Which laws do you use?
Where is it? Here. So this is a realistic, I mean, not realistic, this is a real qubit coupling graph. So this is a 127 qubit chip. It's the Eagle chip from IBM. And they use a heavy hexagonal architecture here. How you group qubits together, so these are, I think, what is it, 12 qubit rings, but they're like overlapping and stuff. If you had, say, 12 qubit processors, you can map them to a ring, map them to different rings. How to do that, I think that I know there's a few papers on this kind of topic and how to effectively parallelize small quantum runs on a large quantum processor. There's all sorts of optimizations that can be done. There's definitely all sorts of factors that go into how you pick them. But I definitely know that the connectivity and the constraints of the hardware must be priority there. But beyond that, I mean, there's error profiles between the couplings, between the qubits. These are also probably factors into that optimization as well. I've not studied this personally, but I do know that there are intelligent folk out there who are studying this, and there's probably a handful of papers on that.
And my next question is, how do they, if we know, but if we don't know, that's okay. How do they solve the problem of error corrections, entanglement? Because I know that error corrections or entanglement is a big deal. Like, it's causing noises, and it doesn't prevent. It prevents the building of a perfect quantum computing. So how do they solve those issues? Or what ideas are there to solve these issues?
So, error mitigation, error detection, error correction. There's a few other error suppression. There's a few other terms for this. They all mean slightly different things, but error correction is kind of the holy grail here. It is a very difficult problem. How people have solved it, I don't think it's a fully solved problem, but I think that there are plenty of solutions out there. Different companies are going with different methods that look at different things. I know surface codes are a big one. There's a few other ones that are, I'm forgetting the names of them right now. There's a few other ones that are gaining traction nowadays. It's a very important field, and there's a lot of very smart people studying how to do that and how to realize that on quantum computers. I don't study that, and I am, not an expert in that field to really go into detail about error correcting codes. But you're right; it is very important. It is very important. So error correcting is slightly different than error mitigation. Error mitigation is more along the lines of how can we, mitigate the appearance of errors, try and produce shorter circuits, maybe you do some averaging or something along that lines that we just talked about, such that you can reduce the impact of errors or not make them come up. Error correcting is a completely different thing where you're actually correcting, like you detect the errors and then you correct them. There's all sorts of different methods and different things for that, but this is out of my realm of expertise.
Thank you so much. I do appreciate your presentation.
Yeah. One other thing I want to add to that thing about parallel quantum computing. So in classical parallel systems, there's a lot of fun problems, there's a lot of things, but an idea in parallel systems is that you are working with multiple different computation units to solve the same problem. Like they're all coming together, there's some reduction, there's some aggregation, there's something along that line, right? There's communication, there's synchronization potentially. I mean, there's all sorts of, but they come together, these computational resources, computational nodes will come together to solve the same problem. There's some dispatch, there's all sorts of fun stuff. I love parallel systems. But the example that I brought up was actually distinct from that in the sense that, and I want to just highlight this, is that those, you're taking separate programs and running them on the same machine. This is more like a Slurm type scheduler problem than it is a parallel runtime type problem. I just wanted to make that distinction, that correction there.
So sorry to interrupt. You mean that in the quantum computation, so when you have a distributed qubit, there isn't communication between the distributed qubits, like in the classical computer, like the MPI. So you mean that they work as discrete solutions, not as shared problems solving?
So no, in the example that I brought up, which is trying to draw analogies to multi-core, in distributed quantum computing, yes, there's definitely like this communication that happens between, disconnected chips that are solving the same problem, 100%. I even know, I think there's like some quantum MPI, some really cool work in that regard. But the notion that I was bringing up was like, if you have, say, a bunch of small circuits and you want to put them together, they're individual programs, you want to put them together to make efficient use of a big quantum chip, right? Because it would be kind of a shame. I mean, not really. Sometimes it's very useful, but if you could take, say, a 3-qubit program and run it on this 127 qubit, well, you're not using a lot of the qubits. So if we can run multiple of those 3-qubit programs, get the results, split them up, and send them to their corresponding parties as if they were just executed individually, there's a whole bunch of scientific endeavors in that regard. But these are distinct. Yes, in distributed, you do have a lot of different qubits that are all communicating to solve similar problems or the same problem. And you're trying to take a big thing and map it over multiple chips. There's also QC. There's different types of circuit cutting, circuit knitting. There's a lot that goes into how you can do that and how you can make efficient use of that. I just wanted to talk about that one thing, though, that I brought up, which is like, if you have multiple different programs, you want to put them on the same chip. I hope that clarified.
That's fine, thank you.
Okay.
All right.
So I think this will be the. Sorry, go on.
Yes. I don't see more questions now, so I think we can go on. Mm-hmm.
Okay, so I think this will be the last section of the talk. I talked a lot today about what numerical instantiation is, how we use it to do cool things. I haven't talked too much about how we actually do it. This program, QFactor, Quantum Fast Circuit Optimizer, is a specialized instantiation routine for large unitaries. It's really cool. It's kind of our state of the art for big blocks right now. So let's talk a little bit about that. Typically, we take our circuits, I talked about this a little bit earlier, but we take our circuits and we treat them as this mathematical function. We built a cost function out of it. We calculate the gradients. We hand this off to some gradient-based optimizer. More recently, we've been using the Levenberg-Marquardt algorithm implemented in Google Series to run these calculations, and it works really well on small blocks. It's incredibly well. It works incredibly well. As you scale up to bigger blocks, the number of parameters in the circuit, though, tends to scale non-trivially. Just looking at Q-search circuits where you're adding just single qubit rotations with every block, as you go deeper into the circuit, you're adding 5 parameters. There's one that you can actually factor out, because these are 3 parameters each. And then you also have 3 parameters for each starting point. So this grows quite a lot with the depth, and it grows also with the number of qubits. The size of the problem also grows because now these matrix multiplies, the gradient calculations, the function evaluations also scale. This creates some difficulty to scale this to larger blocks. Moreover, you require explicit parameterization in working with SU operators. So I draw these boxes as if they're arbitrary single qubit rotations, but we actually have to represent them as U3 gates or some form of parameterized unitary to handle to work with these general optimizers. This becomes a bit of an issue or a headache if you have higher dimensional qudits, because the number of parameters there scales. Like say you want to work with arbitrary SU operators, then you need more parameters for each block. And you also need to parameterize that, which becomes non-trivial sometimes. If you have bigger blocks, say you want to just work with a block over 3 or 4 qudits, that becomes also a bigger headache to work. So you need to explicitly parameterize them. And all of this doesn't leverage tensor network methods. So we do our function evaluations using tensor network contractions in efficient ways when it's a win. But there are methods in the tensor network formalizations that we can use to do the optimization as well. And so we built QFactor. It does all of that. Let's talk about it. So this is, again, solving the problem of instantiation. The problem of instantiation takes as input a unitary target without loss of generality here. You can also have input and output states. Everything stays the same. But just, I'm going to talk about unitaries here. Takes an input unitary target. This is what you want the circuit template to become. You also have a circuit template. And so we build out this tensor network to start the problem. It lays out the inverse of the target on the left, or on the right, doesn't matter, but we lay it out on the left. And then we put the circuit template. If we don't have parameters for the template, then we can just randomly initiate them. And the idea here is that you want all of this to cancel out. If your template, you find parameters that makes it implement the unitary target, well, then that will cancel out with the inverse of the target. We take all of this and we wrap these wires around in a tensor network method. This is effectively computing the trace of this entire network. Okay, so that's how we start. We lay out that initialized tensor network in the top left. How we proceed is we take the first parameterized gate and we remove it from the network, making this an open network. Excuse me. And we contract everything else around that part. So we end up with this environment matrix here. Let's call it the environment matrix E. And it's the same size as the gate. This is very important for why this is a very optimal algorithm. We then, just take my word on this, we talk about this on the next slide. There is a method, a tensor network analytic method to calculate the optimal gate to put back where this gate was removed. And we call that our gate update. We do it analytically. One gate at a time, very local. So we update this gate down here, and we sweep over all the gates in the circuit, doing the same method. And then we repeat this process until our cost function, the distance to the unitary, or how close this whole network is to the identity, until it converges, till we either get something we're happy with or till it stops improving. So let me explain how we do this update. So we're at this situation, we have this environment matrix, and the question is, we want all of this to cancel out to the identity. So in this context, what is the best gate or set of parameters for the gate that makes this cancel out as much as possible? Formally speaking, if this was G, then this is the argmax of G with the real of the trace of the environment times G. And that's equal to Y times X dagger, where Y and X come from the SVD of this environment matrix. There's a proof in the paper, if you're interested in how this works. It's very important that we take the real here. But that's how it works. Some cool things that come out of this. One, this local optimization, this SVD operation is based off the size of the gates that you're working with. So it's very efficient. Additionally, you don't require any parameterization of the gates. When you do this equals Y times X dagger, you're getting the unitary that this equals. There's no parameterization. So if you're working with arbitrary SU operators of any size for any dimension, it's still the same, Y times X dagger. And you don't need to parameterize it, which is very valuable. And I'll showcase some examples of that in a little bit, where that becomes valuable. So QFactor is, we implemented it in Rust. It's accessible through the Python BQSKit package. We also implemented it on GPUs using JAX. This is a standalone package that you can get to through our GitHub. It's also on PyPy. You can just do pip install of it and plug it into the BQSKit workflow. We find that QFactor is faster with partitions with more than 6 qubits, comparing it to the series methods and LBFGS methods that we've used priorly. And we still use these for small blocks. So QFactor makes working with bigger blocks more practical. All of this stuff is running single-threaded because we use our parallelization resources for other use cases, like the partitioning, the blocks, that kind of stuff. And all of this is running single-threaded, and I think the timeouts here were like an hour or something like that. So we're trying to make sure that we can run these blocks in a practical sense when you have, say, millions of these blocks. Or, the bigger the block, the less there are of them. We find that with the GPU version, we outperform the CPU in greater than 9 qubit regime. And we've scaled this up to 12 qubits due to our timeouts and things like that. We can also potentially push this a lot further, depending on how much resources you have and how much time you have for it. So we can work with bigger blocks, but what do bigger blocks give us? This is a gate deletion workflow. I have a lot of data here plotted. I'll introduce all of it, but we're taking big circuits, partition them into different sizes. On the left, we're running the GPU QFactor JAX. And on the right, we're using our parallel series implementation. This is the one that we used a lot before QFactor. We find that series kind of falls off on the larger blocks. It times out a lot. It's hard to find the solutions. But what we see with QFactor is that going to bigger blocks with these gate deletion strategies with others, it verifies this trend that as you increase the block size, that you get better results, higher optimization opportunities because your instantiation scope is growing. And so you're allowing more of the circuit to change as you remove gates. And so we see a 30% increase in the reduction of gates for some of these algorithms. So QFactor allows us to work with bigger blocks. Bigger blocks gives us better compiler efficacy. Okay. Any questions about this so far?
Actually, there's another question from Jervis. I think it concerns one of the earlier slides. So Jervis, maybe you can unmute because I can see that you have another question as well.
Yes, I have two questions. The first one was when you were explaining the parameters. No, I think instantiations of circuit or qubit. And you mentioned about the parameters. I wanted to I want to know, do you mean variables or something else? And my second question, in QFactor, I saw a postfix named JAX. Can you explain what does it stand for? Thank you.
So parameters are the variables. So remember, these gates are, mathematically speaking, unitary operations. Some of them are parameterized. Like, so I draw a block here, but you can think of this as like a U3 operator. There's a formalization, I think it was defined by IBM, where, you know, it's like some phases times like cosine of theta. There's 3 parameters, and it builds up a 2x2 unitary matrix that you can, this gate represents. And it's a 3-parameter thing. So this concept of instantiation is trying to find, for all of these gates, they're parameters, they're variables, they're all independent. We're trying to find the values for those parameters that, you know, minimize some cost function. That's what's meant by parameters. In terms of JAX, JAX is, I think, software built by Google. It's really cool software. You can kind of handle it like NumPy. And it can be JITted to GPUs, to CPUs, to all sorts of things. So we used it as a framework to build out our mathematical, you know, algorithm here and distribute it over, or JIT it to a GPU very efficiently. I didn't write the software. The software is publicly available online. Alon Kukliansky wrote this. He's part of the team, and I'll showcase the team in a little bit. If you're interested, you know, take a look at the GitHub repository, take a look at the JAX library. I think it's really cool software. A lot of people are using it to do really cool things. And if you have any questions, reach out to me or Alon. It doesn't stand for, I actually don't know what it stands for, to be honest. It might stand for something, but yeah, I don't know. Yeah, QFactor JAX can be read like the GPU version of QFactor for the sake of these slides.
Thank you so much.
Okay. So I talked about not requiring explicit parameterization, and there's a really cool thing that allows us to do. Let me illustrate that with an example that led to an amazing workflow for circuit resizing. So let me introduce circuit resizing first. We have some circuit. What we can do, if the circuit structure allows for it, is we can take, we can map this logical circuit to a physical circuit that has fewer qubits than what is required by the algorithm. This is definitely a toy example, but it showcases it very well. That you can, by inserting mid-circuit measurements and resets at certain points in the circuit execution, that you can actually reuse one physical qubit for 2 logical qubits. This can be done multiple times, depending on circuit structure, when it's allowed. There's strict requirements on when you can and can't do this. Basically, you need a portion of the circuit. You need to be able to schedule the gates in such a way that to the left of some line, you're not using one qubit, and to the right, you're not using the other. Let's take a look at this example here. Not all circuits are resizable, though. This circuit is not. There's no way you can schedule the gates in such a way that it is resizable. But what QFactor allows us to do, and what we've demonstrated with this work, is that we can use this higher dimensional SU operators to write a circuit template very quickly that parameterizes all of the possible resizable circuits. Like if there is a resizable circuit, then it looks something like this, where maybe these blocks are expanded out to different gates. And we try and instantiate this to the original function of the circuit. This is more or less a physical process that answers the question, can the circuit be made resizable? And it's a really quick and efficient way to do this, because QFactor can handle these formalizations very efficiently. 2 gates, it treats each unitary, no matter the size of it, as quote unquote one parameter. Very hand-wavy concept there. Because while it is just, each time it does the gate update, it's doing an SVD. And so if you can instantiate this to the original function, then you can always resize it this way. Right? So this parameterizes all of the possible ways you can do that. We built this concept into a full workflow. There's all sorts of other considerations that we did, like how do you downsize these, how do you make it more efficient, how do you then, once you get these blocks, actually compile them to native gates. There's all sorts of cool things that we did there. If you're interested, take a look at this paper. Again, all of these papers that I'm linking, if you missed them, I'll have a link at the end to our website, biscuit.lbl.gov. We have a publications tab. All of them are listed there. One other thing, just to highlight this, is that QFactor, the point here is that QFactor can be used to answer well-posed questions about circuits incredibly quickly, and that's really useful. We're currently working on a new method related to distributed quantum workflows with the question, given a boundary block, what's the minimal number of remote operations between the 2 QPUs that is necessary for that unitary? And we can do this using QFactor. We can do it very quickly and very, very successfully. If you're interested in this, stay tuned. We should have more coming out soon about that. The last real data slide that I have here, I want to showcase something that is really cool. Having worked on these algorithms and this project for a very long time, it's been amazing to see where we've started and where we're at now in terms of how much we can do. Not just in the algorithms and the applications, but also in the execution time of these things. When we started, QSearch was taking, for 3-qubit instantiations, 3-qubit synthesis, was taking on the order of hours to days. Now we're doing 3-qubit instantiations in fractions of a second, and we're still improving. There's a lot more engineering that needs to be done to improve. There's many different methods that we're looking at. Here we're looking at a graph that is showcasing a new method. It's a completely whole new paradigm in thinking about unitary dynamics in compilation. This idea comes from Lukasz Szczęsio at Los Alamos National Lab, and his group, where they found that you can use only a handful of states and learn on those. It's a QML concept, to learn on those as data points, and as a result get the full unitary. You can learn the full unitary dynamics with only a handful of states for a wide variety of useful circuits. And so we took this, and with a collaboration, and we implemented a improvement to QFactor. This is coming out soon. QFactor sample, where we're able to, instead of working with the unitary, the full unitary, work with a very cleverly selected subset of states on the order of 2 or 4 or 8, and thinking like 12-qubit circuits where you would need 2 to the 12 number of states to get the full unitary dynamics. We're able to actually do these algorithms on just those handful of states and learn the full unitary as a result, which is, I've been working on this for a while. Alon's been leading this project. He's been doing this for a while, and it's still kind of awing to actually see that actually happen and get good results out of it. And this graph shows the scalability of what we're able to get with that. It shows a paradigm shift in the scaling of these algorithms. This is the 4 to the x that you would expect out of full unitary dynamics and QFactor jacks. As we increase the block count, these are like the average over a wide variety of different algorithms, how long it takes to do these instantiation calls. Where with this QFactor sample method, we see this asymptotic improvement. This is 2 to the x. So this is I think amazing. This is coming out soon and will be rolled out into all of BQSKit over time. With that, I do want to say thank you to everybody, but also thank you to the team. I'm just one person, part of a big team that's multi-institutional. There's no way that all of this work gets done without a great set of people to work with. We're across the lab, across a handful of different universities, and we have a wide range of experience levels from undergraduates that we worked with to senior scientists and senior engineers. And it's just been amazing to be part of this team and to produce this work. It's also great to say that among our past members, students that have gone on, we've seen positions. It's great to say that we have a lot of these past members at great positions, at great companies, see senior scientists, senior software engineers, professors. So, I mean, this is, I'm just one of many here to present on behalf of this big group. With that, I'm going to say thank you. Here's the link again. You can get to everything I've talked about, publications, documentation, code on our GitHub through this link. You can use BQSKit very simply by just importing a CASM file, compiling it, and then saving it. There's other ways to load circuits. We have a tutorial online. Want to acknowledge our funding sources from ARQC on DOE and Oscar. We're very happy to collaborate. If you have an idea that you're interested in exploring with BQSKit, please don't hesitate to reach out. If also on the flip side of that, we take GitHub issues seriously. If you want to yell at us, tell us that our software sucks, that we did something wrong, please do it. We love that. The GitHub issue, the issue tracker is a great place to voice these things and also ask for improvements, to talk about your specific use case. We'd love to hear that. But also don't hesitate to email. I also want to plug that I think we're hiring as well. So don't hesitate to reach out. Thank you very much. Thank you for your time on this Sunday, and I'm happy to take any more questions here.
Great, fantastic. Thank you very much, Ed. It was a pleasure for us. And as Anne has said on our chat, it was an outstanding presentation. We had many questions during the talk, but let's see if there are more questions.
Actually, I saw 2 more questions on YouTube. Let me post them on the chat.
Okay.
Can I ask how many people are watching from YouTube? And how many people are watching from Zoom, just out of curiosity?
Right now, 16 people on YouTube, excluding me, is 17 people on YouTube.
And here
Awesome.
on Zoom, we have now 23 participants, so together with us, with the organizers, but there was a point in which we had about 30. So.
Oh, wow, that's awesome.
Okay.
Yeah, thank you.
Yes, we have some questions on chat. So the next question from Jervis. Yeah, so he's asking how to reach out to you. He's looking for a job in the US.
Oh, yeah, my email is edyunus@lb.gov.
Maybe you can later, post it on chat as well. Or maybe we can send it to Helen, and Helen can distribute potentially.
Yeah, that's very, very fine.
Okay, good. There is a question from YouTube. I think quantum computers are analog machines compared to the digital machines. Is the difference of a major impact between the classic and quantum computers?
So, question. A lot of what I talked about, and I think everything I talked about today, was with regard to digital quantum computers, in the sense that they're gate-based. They're executing discrete gates. But there is an analog quantum computing model, and we are actively exploring and interested in exploring further this way and how we can take our tools to improve it. There was some recent work that I thought was really cool. I forget who it was from. I have the paper saved somewhere, but it was looking at a combination of analog quantum computation and digital quantum computation for different steps in the algorithm. And this definitely gave us a lot of food for thought. It's very interesting work. So, I mean, analog quantum computing is, I think, really cool. You're right in that these computers are inherently analog. and that the discrete nature is kind of imposed on top of it, depending on the hardware model. But there is a lot of use cases where you can kind of break these abstraction layers and get good results. But I think it really definitely depends on the hardware. I know that neutral atoms are able to break that layer a lot easier, that the exposing the analog computation to the users is a lot easier, a lot more natural. Where superconducting, as far as I've been told, is that with superconducting devices, that the digital layer is a pretty good abstraction layer, that working with the gates that are calibrated and fine-tuned is valuable. But nevertheless, there's a lot of works that break those abstractions and look for good improvements, especially in the NISC era. You got to do everything you can to get the best results.
All right, thank you. There's another question from YouTube. Let me just go up. Yeah, why Q-search circuits need 5D plus 3N parameters?
Good question. So the 3N comes from, if N is the number of qubits and D is the depth, the 3N comes from the first initial layer, right? So we put single qubit gates along each initial layer. And this is based off of like the most default Q-search. If you fine tune Q-search, your different gates, things will change, but it does give you an idea in terms of how many parameters are necessary. So the 3N comes from this initial layer of single qubit gates. Each of these is 3 parameters, and there's N of them, so 3N. Plus, for every depth, you have, I actually think it's 4 now, but with each block that you add 2 U3s with a C0. This is actually out of date. Yeah, with our newer, some point a while ago, we dropped this down to 4D. But each of these U3s, these 3 parameter gates, requires 3. So you'd start with 6. But this 5D comes from the fact that you're able to factor out, you're able to break this U3 down into, I think it's like a ZYZ, and factor out a Z this way, or Z up here, I forget. And with this one, you're able to break it down in a different way and factor it out. But this 5D doesn't consider factoring one of the parameters to the left in the top, I think. But yeah, our most recent ones are doing 4D. So we're able to take these 6 parameters, break them down into 3 gates each, factor one of them to the left. And if you do that across the whole circuit, they all kind of factor all the way to the left and congregate in this initial layer. So you end up with 5 in this example, but this slide's out of date, 4 in reality parameters per block. And that's D is there's D many blocks.
Okay, thanks. There's another question, or actually 2 questions from YouTube. What would be the downsides of such an approach? Would not mid-circuit measurement impact your computation in any way, or any other issues that would consider? And as a follow-up, would you see this approach be applicable to error mitigation?
Specifically, what approach? Sorry, I might have misunderstood the question.
I don't see any information because it was asked on YouTube, so Helen just pasted it. But maybe the author of this question from YouTube can maybe send some details regarding the specific approach.
So while we're waiting there, I can speak generally to the question. I think is that you get error mitigation strategies kind of holistically from just reducing the number of resources that you use, because as you use more resources, you're going to acquire more errors throughout the circuit, and that is technically a form of error mitigation. The approximation method is a direct form of error mitigations where we're taking circuit averaging to another level to reduce the number of errors in a circuit, or reduce the occurrence of errors by trading controllable synthesized errors for hardware more or less uncontrollable errors. I think the question, there was a measurement-based quantum computing involved in there, or did I mishear that?
What would be the downsides of such an approach? Would not mid-circuit measurement impact your computation in any way, or any other issues?
Yeah, that's a great question. I understand now, I think. Hopefully. The mid-circuit measurement definitely is something that it has a cost to it. If you look at the paper, we examine the cost of this. We run these on hardware to make sure that we're getting improvements. Like you could technically try to resize this 5, 6, 7, 8 times, right? Say you have a circuit, you insert 20 different mid-circuit measurements into the circuit. Then, yeah, they have a cost associated with them. Definitely, the measurements are not cheap. In fact, they have a long time to execute on most hardware, and they also have they introduce a lot of errors in the sense that, if your frequencies of your qubits are very close by, you might be measuring one or similar ones, and there's all sorts of stuff that happens. This has to be included in a model in how you do this, right? So this parameterizes all the possible circuits that are resizable, with Q0 and Q3 being the ones that you're mapping onto the same physical qubit. But you can actually vary that. You can vary how much you do it. There's a whole, there's a depth to how we pick these qubits and how we find where we can resize. Yeah, if you do this naively, you're not guaranteed to get a win by just reducing the number of qubits. But if you're very careful about it, in a lot of cases, you can actually do get some wins here. But yeah, it's a great question. This is definitely something that needs to be incorporated into this. But there's also a resource trade-off in that why we're able to actually see wins is because in a lot of cases, by doing this mid-circuit measurement and the resized circuit, we're even further able to reduce the number of CNOTs in each block by quite a significant amount using these synthesis tools and QFactor and this kind of stuff. And so we get a resource reduction in this case, usually not only in width, but also in depth. And that's kind of where we get wins from.
Good. All right. I don't see more questions on our chat now. So let's maybe give a few more seconds. Maybe someone would like to unmute and ask.
I do have one last question. For an HPC quantum accelerator in that stack, are you working with people that are working on that whole, I guess, building that whole thing out as a resource? And this compiler section in the stack, are you working with them, or is this something that can take over that whole section of a accelerator?
What do you mean by accelerator? Like you're combining HPC and quantum together in kind of like one roof? And
yeah, actually, yes, actually using quantum computing to accelerate the HPC. So as a node, where some people, you can use it as a node to accelerate one part of it, but you can map that out even further. And how do you optimize where you're placing that, how you're placing that, the communication of them? I mean, it's very complicated. I know a lot of people are working on this, but this fits right into that stack. This is one of those elements. So I was just wondering, are you like the vendor, one of the vendors for that part of the stack, basically?
I wish I was a vendor. So we don't directly work, at least I don't directly work with this combination of, HPC, HPC accelerated by QC. There is like an inverse to that, which is, QC accelerated by HPC, and we are trying to, that is in essence what we're doing here. You can run these things on your laptop, but you can also scale up to HPC type things and get, as you get more computational resources, you're able to use more heavy grade optimization procedures and get better results. The NERSC, so this is the Supercomputing Center at the Lawrence Berkeley National Lab, work very closely with them. I know they do have their eyes kind of set a little bit on, exploring that possibility of integrating QC into HPC. And you're right in that there is a lot of challenges and potential opportunities for integration and co-design between the compiler and these kinds of HPC and QC systems. There's great software out there that looks at this, like XACC. I know Oak Ridge National Lab there's a lot of fantastic researchers over there who are exploring this. I've had discussions with them about this in the past, but I'm not an expert in this area. But you're right. I do think that there is a lot of potential for collaboration and tight integration between the compiler and a QC accelerator in an HPC setting. But yeah, I'm not a expert or currently actively exploring this area.
Thank you. I just also want to say, great presentation. A lot to think about, a lot of great stuff. Really appreciate it. Thank you.
Thank you very much for the questions. Happy to be here to present. If there's any questions that come up now, I'm happy to take more. I'm also, in the future, if questions come up, collaborations, please don't hesitate to reach out. I promise I won't bite.
Good, great, fantastic. Do we have more questions to add? Last chance. All right, I think that's all for today. So Ed, thank you once again for this great presentation and answering all the questions. I believe we've learned a lot and it was a fruitful discussion. And yeah, and our participants just give very positive comments. So yeah, thank you for this. Thanks everyone for joining today. And as you may remember, we'll have the next meetup on next Sunday. So we hope to see you then. And Ed, we also hope to have you as a speaker in the future next time.
Always happy. Thank you very much for the opportunity.
Thank you. Thanks.
Take care, everyone.